Hello everyone, my name is Anthony Shivkumar and welcome back. And today we're going to dive into the attention mechanism from the GPT-2 model. And the modern models now have, group query attention and other details that are slightly different, but understanding the GPT-2 model will give us the insight that can help us understand the newer models. So on that note, let's get started. So in this particular video, we're going to go through the attention is all you need. So it's an incredible journey, from the mathematical theory behind attention mechanism all the way to the production grade C code that achieves, around 400 gigaflops is something that I will show you towards the end, the demo. And this isn't just theory. By the end of this presentation, we'll have a deep understanding exactly how to build world-class attention implementations. So we're going to process through, these 5 distant phases. That is the theory, the intuition, the architecture, and the HPC, the high performance code, and finally the production of how do you deploy this. So we'll start with the famous, query into key transpose formula and end with the code that achieves the performance comparable to the best implementations. So in part 1, the mathematical foundation, let's begin. We're now in the theory phase of this journey. It's crucial to understand that these mathematical building blocks before we move to the implementation. We just need to understand not just what the formulas do, but why they work. And this mathematical understanding will inform all of our optimization decisions later. And without this foundation, I think we'll be kind of like optimizing blindly. So before attention mechanism sequence, models were fundamentally limited by, the traditional RNN. They had to process the sequence one step at a time, and that was around, OT in terms of time complexity, with no possibility of parallelization. And they suffered from information bottleneck, where all context had to squeeze through hidden states and gradients. Vanishing problems meant they couldn't handle long sequences effectively. And then self-attention changed everything by introducing parallel processing, which is again OS to 1 time complexity. And if you have enough cores, it creates direct connections between all positions in the sequence with constant path length for information flow. And the core insight is revolutionary. Instead of sequential hidden states, we compute attention weights between all pairs of positions simultaneously. Now, for each token in our sequence, we want to create a new representation that is weighted average of all the other tokens. And the key insight is that these weights are not fixed. They're calculated dynamically based on how relevant each token is to the current one we're processing. The formula is output I, which is equals to the sum over all j of alpha ij times value j. So here we're basically taking the aij of all the different types of the tokens, and basically kind of like summing this up. And where alpha represents, how much tokens I should attend to j. And the fundamental question becomes, how do we compute these attention weights alpha? And that's what we'll explore over here. So this is just a very simplified high-level stuff. But before we get into the real details of the 4 steps of what really happens in the attention mechanism. So in this step, which is projecting inputs to QKV, which is the most important thing, we've got the query key and value for each of these different types of every one of the inputs. Every one of the tokens will have their own query key values, and we want to know how they attend to each other. And this is kind of like the formula that helps us kind of like create the evidence in some shape or form of how each token or each word, has information with respect to the other tokens. So the first step is to transform our inputs into 3 distinct matrices. So in attention, there are a few steps to kind of like do the whole attention mechanism. One of them is called the QKV projection. So first and foremost, we do the QKV projection. So we start with using our input tensors and project it using the learned weight matrices. So Q equals, X times the WQ, K equals, X times WK, and V equals X times WV. And these are all the weights that are trainable parameters. The X, the W over here, and X is the input, which comes from the previous layer norm output. And X has a dimension of T by C, for example, that would be 2048 tokens. That would be your X dimension, and the number of channels or number of features or your embedding dimension, say for example 512 over here. And the weight matrices WQ, WK, and WV are all C by C, which is basically 512 by 512. And these are learned parameters that the models updates during training. And the output QK and V matrices are all of type, T into C. T is basically the number of the context length versus C is the embedding dimension. And this is our first major computational step. And these three massive computations can be done through a general matrix multiplication, the GEMM kernel that we spoke about earlier. And these projections transform the input into query keys and values that will be used for the additional computation. So this is the first major computation in a series of few things to get the attention working. Here we are splitting, once we have the query key attention, then we have to split into multiple heads. And to allow the model to focus on different types of relationships simultaneously, we split the Q, K, and V matrices into multiple smaller heads. We go from one large Q matrix of dimension, which is embedding dimension by the number of, by the context length multiplied by the embedding dimension, T by C, to the heads. And each of the dimension now is basically the context length by the number of heads, or the head dimension, basically. And this gives us a new structure with dimension h by t by dh. Typical values you'll see in practice are C is just total dimensions and might be 512 or 768 or 1024. H is the number of heads, is typically 8, 12 or 16, and that, as far as I'm concerned, it really depends on the way you're computing. And I think it really depends on the cores. If you're designing this from your grounds up, you might want to design it based on the cores that you have, the number of computes that you want to fit this as per the hardware, so that you can parallelize this whole thing. And those are the details that I'll talk about, in the later part of this video or in future coming videos. And the dimension head per head, which is 64 or 96 or 128, where C equals h times dh. And each head can learn to focus on different aspects of the relationship between tokens. Some might focus on syntactic relationships, others on semantic relationship, and so on. So what we're doing over here is creating this kind of like matrix multiplication, where each part of each token and they sub dimensions, or their head dimension in this particular case, can attend to different parts and create some meaningful extrapolation of whether it's semantics, whether it's structure, whether it's translation, and these are all emergent properties of gradients when you do the training. So here we have the overall, kind of like the dimensions of what the head might look like. And now we do the scale dot product, which comes back to the pure attention mechanism, which is now this is the core calculation, and it's performed independently for each head. The formula is attention of Q multiplied by QKV equals softmax of Q into K, Q multiplied by K transpose, and is divided by the root of the dimension, divided by the square root of the dk, all multiplied by, and then this whole thing is multiplied by V. The dk is your head dimension. And let me break this down into the components. First, we compute the score, which is with Q multiplied by K transpose. This tells us how much each token should attend to every other token. Then we scale by 1 over the square root of the dimension of the heads to prevent gradients from vanishing. For decoder models, we apply a casual mask to prevent looking at future tokens. We normalize with softmax to convert scores to probabilities. Finally, we compute the weighted sum by multiplying by V to get the final output. So this is kind of like the steps that we have, right? And in here, when we do the softmax, we kind of like have a casual, so we only kind of like zero out or infinite, make the the top of the triangle kind of infinite, so that only the current token can attend to the previous token and not to the future tokens. And if we do attend to all tokens, that's self-attention, and that's something like what BERT does, embedding models do. But for autoregressive tokens, you just want the latest token to only attend to the previous tokens. So this is what would happen in the actual a matrix that's happening in softmax. As I mentioned, the top dimension is kind of like, you don't need to calculate them. We're only making sure that this token is only attending to all the previous tokens. So in this step 3a, calculating scores, visualizing, let's visualize how we calculate those attention scores. We compute a score matrix by taking the dot product of the query matrix with the transpose of the key matrix, and the Q head with dimension T by dh, which is the number of the context length or number of tokens multiplied by dh, which is the head dimension. the transpose will give us a score with dimension t by t. So eventually, once you do these two matrix multiplication, you'll have basically context length by context length in some shape or form. So that means each token can now attend to the other token. Now this tells us how much each token should attend to each other token in the sequence. The formula for each element is score ij equals the sum over dimension d of qid times kjd. And this is pure GEMM operation, a matrix multiply, which is perfectly suited for optimization. The visualization shows how these matrices multiply together to produce the attention score. So this is the standard formula for attention. But what we can see from here is that you're taking these part of these dimensions and creating and seeing how each token attends to the other token. And last but not least, once you have for each head, then we have to, the final step is to combine all the heads output back together. The outputs for all heads are concatenated and then passed through a final linear projection layer. The formula is output equals concatenate of head 1 through head h multiplied by WO. And here this is the projection of the attention, which will be the last step. And this is the fourth and the final, kind of like GEMM operation in the attention mechanism. After these projections, we have our final attention output with the same dimension as our input. And now we understand the mathematics, but the key question is how do we implement this efficiently? And that's what we'll explore in the next session. So let's build our intuition right now. Intuition memory arc. Now we're moving from a theory phase to the intuition phase of our journey. In this section, we need to understand why the mathematics works the way it does and how to architect memory for maximum performance. This is where we bridge the gap between mathematical understanding and practical implementation. We're starting to think like performance engineers, not just mathematicians. So this is the decisions we make here about memory layout will determine whether our implementation runs at 10 gigaflops or 400 gigaflops kind of a thing. So let's go into now, where exactly in this whole process of the AI is our attention, is the computation. So the heart of the transformer, let's put attention in context with the full transformer architecture. The transformer has many components, embeddings, layer normalization, attention, residual connection, and the multi-layer perceptron, MLP. But here's the key insight. Multi-head attention is where I would say a good chunk of the computation happens in a transformer. This makes the computational bottleneck and the most important component to optimize. I would also say even including the multi-layer perceptron, and the head is these are the two major computations that happen, because here you're doing tokens multiplied by all tokens, whereas here you're doing it for the most part. Every other computation only deals with the latest token. So this makes it the computational bottleneck. And if we can make attention fast, we've made the entire transformer fast. Understanding its current implementation is absolutely crucial for performance, and this is where we need to focus all our optimization effort. Our implementation strategy, which is the head parallel with smart memory layout. Our implementation uses head parallelism as the primary strategy, with dynamic head memory layouts transitioning to optimize each computation phase. We have 4 distinct phases. Phase 1 is the QKV projection. We go from token parallelization to head major output, and then phase 2 is the attention scores, head parallel input to head parallel scores, and then phase 3 is the concatenation, and then head parallel input to token major output. And the key insight here is that the head parallelism provides the best cache locality for the compute-intensive attention phase, while we adapt memory layouts to optimize each stage. This strategy is what enables us to achieve world-class performance on CPUs. So there's a lot of memory, kind of like kung fu going on over here, so that we can constantly make the caches hot and minimize eviction. That's really what my research and analysis is all about when I'm designing this from CPU from the grounds up. So the foundation of memory, now let's talk about the memory layout, which is the foundation of the performance. We need to map the logical concepts of head to a physical memory layout that the CPU can process at maximum speed. Now logically, we think of 8 separate heads that operate independently, but the physical reality is different. We use a head major layout where each head data is perfectly contiguous in memory. So because they're all perfectly contiguous in memory for this particular head, then that means each one of them can be also moved to different cores, and that's really what we're looking at. So this could be all in different cores, so they can be processed parallelly in server grade CPUs. So this layout is head, then token, then dimension, and all data to the All data for head 0 is contiguous, then all data for head 1 is contiguous, and so on. So this enables perfect cache locality during head parallel processing, and when we're processing head 0, all of its data fits in cache without interfering with other heads. And that's really what we're trying to kind of like get, is can we get the maximum speed with our design that we have over here. And the head major reorganization, this reorganization is not a simple transpose, it's a deliberate out-of-place reorganization of data of performance. We transform from input Q tensors with dimension T by C in token major layout to output Q buffer with dimension head by, tokens by dimension head in head major layout. And for example, if this is all tokens, we kind of like, I've kind of like divided this into only the head 1s, head 2, head 3, head 4, and taking part of the embeddings of that particular token. So when you concat them, you'll get the full embedding dimension of that particular token. But in memory, this would be like one section, and then this would be the next section, this would be a next section, this would be a next section. So for each head represented by different colors in the visualization, we gather its feature columns from all tokens and write them into a new contiguous memory block. The performance impact is huge. Instead of scattered memory axis where we're jumping around in memory, each head's data is contiguous. When processing head 0, the entire head fits in L3 cache. This is key to our performance. And here we go to the memory architecture. We're entering this particular phase. Here we see that the actual C code structure and memory architecture that enables around 400 gigaflops performance is where theory meets kind of reality in terms of data structure and memory management. So we're going to see exactly how we organize memory at the C struct level to achieve maximum performance. So I will be walking through a lot more even into the actual code, but here is what we have is our memory architecture uses a single contiguous memory block with precise struct level control. The key design principles are single allocation. We do one huge malloc for the entire model, avoiding fragmentation. Cache alignments, all major tensors are aligned. This is basically how we have kind of like done this. So we've separated QKV. If you're doing GPUs, they normally put QKV as one little tensors. Under Karapati has done that too. But if you really want to get maximum speed and you want contiguous memory, compute, contiguous data to be residing on your DRAM and fetch, more streamlined, I found out that you should separate Q, K, and V as separate tensors and let them, stream independently. So that the CPU knows that it's streaming Q, streaming K, and streaming V, and there is no and all of Q is contiguous, all of K is contiguous, all of V is contiguous. So that way we can there is no cache evictions and cache misses. And all major tensors are aligned to 64-byte boundary, so everything is aligned. So we know that there should not be fault sharing. And head major layout, contiguous memory per attention head. We also have Canary protection, so in case, if we can detect buffer overflows. So zero fragmentation, completely predictable memory access patterns. The result is around 95% L3 cache hit rate. At least that's what we're trying to get. And the truly optimal layer struct shows how we can track precise memory offsets for every tensor. And the transformer model struct manages the entire model with aligned dimension and execution planning. And this level of control over memory is what separates a toy implementation from a production one. And here we have the head major access. The performance key here is we see the careful designing macros that enable. So we have QKV and the attention access. We have the macros designed in our code. It's all available on GitHub. So go have a look at C Transformers on Anship Robotics GitHub. And all of these macros allows us to kind of like, fetch all of this data at the very specific pointer location. So our head major memory layout follows this pattern: head, then token, then head diamond. In memory, it's organized as head 0 with all its tokens, then head 1 with all its tokens, and so on. The access macro QKV handles tensors access, while attention access handles attention scores with the pattern head, query token, and key token. And why is head major so important? Because each head's data is contiguous in memory. When processing head 0, all its data fits in L3 cache. There are no cache conflicts between heads during parallel processing, and this is absolutely critical for performance. And now we'll go to the memory flow deep dive. We're now entering the HPC, the high performance computing part, the best part of everything, a phase of our journey. In this section, we'll see exactly how data flows through memory and cores in each computation phase. This is the detailed execution model that achieves high performance. We'll track data movement, core assignments, and cache behavior through each phase of the attention mechanism. QKV projection, memory flow, phase 1. that it transforms, from token major to head major. So this is all done in one step. So while we're reading over here, we're writing it in very specific memory regions. So this is kind of like what's happening over here. We're not doing two steps. We're reading over here, and the output is stored at a very specific memory region. And this is kind of done deliberately. So this process might be slightly slower than storing it into, in a more contiguous way. But in the overall attention mechanism, when we do this, the speed is significantly better, because then we don't have to spend a step of, making this contiguous. So when we write it, we might have a little bit of, kind of like a slowness in here. But in overall attention, the memory, the speed overall, is much faster. So the individual components might be slightly slower, but overall it'll be much faster, because we don't have to do any more memory manipulation when we write in a way that it's all contiguous as per head major. And here we have S0 contains all the tokens from T0 to Tn for that, and with their embedding size or head size. And for core assignment, each core processes a slice of tokens. Core 0 handles tokens 0 to 255. Core 1 handles core tokens 256 to 511. Yeah. And each core processes token slice in all heads. So the AVX-512 computation shows directly what, shows direct right to head major layout. So we're basically taking the, the queue and the key. The direct right to head major layout avoids expensive transpose later. That's really what we're trying to get at. And this phase prepares the data for efficient head parallel processing in phase 2. So we're going from token parallelization, but saving it as all head in the memory. And the attention score head parallel perfection phase 2 is where most of the computation happens, and is perfectly organized for head parallel execution. Both input and output are in head major. So here now we've got an head major, and now all the heads can now be in parallel in the core. And because of this, both for one assignment, each core handles one completed head. Core 0 processes head 0, core 1 processes head 1, and so on. And each core computes the complete Q times K transpose for its assigned head. We achieve perfect cache locality because each core's head fit entirely in cache. And the AVX-512 computation uses nested loops over tokens with, fuse, multiply, and add instructions for maximum throughput. So this reduced add. So we're setting everything to 0. We're doing the accumulation. There's a fuse, multiply by add, the FM and add, and then you reduce all of it. So we're storing all of this in accumulation, and then it will reduce it into one number. And this is why the head major layout is so crucial. It enables the perfect parallelization. And then the concatenation from head major to token major. This is a very quick step. So we're just basically concatenating again all the heads to form all the token embeddings back to the original dimension. And the output is token major, where each token contains data for all the heads. Core assignment returns to token parallel. Each core handles a slice of tokens, gathering data from all heads. Core 0 handles token 0 to 255, gathering from all heads, and so on. This is a memory reorganization phase with conservative threading due to memory bandwidth limits. And now you might say, why don't we just directly skip this step? I found this step actually speeds it up and not slows it down. So that's the reason why I added it, and instead of, directly writing it into token major, it just happened to be slower. So doing the concatenation happened to be faster. And in this phase, it's primary memory bandwidth limited, and each core gathers data for its assigned token from all heads, which requires careful memory access patterns to avoid bottlenecks. And here we have the final projection. Token major efficient phase 4 is the final projection, a standard token parallel GEMM operation. Both input and output are in token major layout. Each core 0 processes a slice of the token. Core 0 handles token 0 to 255. Core 1 handles the remaining, and so on. And this is a standard token parallel GEMM operation with AVX-512 instructions. And we get excellent sequential access patterns because the data is already in token major layout from phase 3. And this phase benefits from the memory layout established in phase 3. It's a straightforward parallel GEMM operation with good cache behavior. With the sequential access patterns means we can achieve high memory bandwidth utilization. Now this is all very advanced stuff, so this is not a beginner on AI. So if you want to know exactly how attention works from a much more fundamental standpoint, there are much better resources over here. This is purely from a high performance compute standpoint, these types of slides are. So pardon me if a lot of this is may not make a lot of sense. So, and lastly, we'll go to part 5, which is the production code. We'll finally reach the production phase of our journey. This is where everything comes together, the real C code that achieves 400 gigaflops performance. We'll see working optimizing code that integrates all the concepts we've discussed. This is in pseudocode or simplified examples. This is actual implementation that achieves world-class performance. So before we go over here, I'm just going to take you directly to the code itself. And here I have the full working transformer at this point in time as I'm recording it, but I will just focus on the attention mechanism today. I have full parity with full inference with PyTorch, but today I'm just focusing purely on attention mechanism. So here I want to talk about the number of heads. Where is the thing? Yeah, so we have divided the SQV, the QKV, the query key and value into different this is for the QKV projection. Then we have the attention scores, and then we have the projection weights. So we kind of like split this up into a few major sections. And then from here we've got the memory layout of how we are kind of like using the bump allocator for QKV offsets. Then we have the weights and biases for each of those, and then we do this for the projection as well. So we have the QKV projection, and then we have the Q, we have the K, we have the V projections, then we have the attention score bump operator, and then we have the final projections and the attention. So this all is part of the attention mechanism. So I've just separated Q because I want to have Q as to have a very nice clean little stream of reaching the L3, L1 cache, the K and V. And if you're doing this on GPUs or NVIDIA accelerators with 3D tensors, you can interleave the QKV, which is a lot of what many people do, and they try to do that on CPUs, and it's actually a very horrible performance because now you're having cache evictions. So there are certain things that you can't just directly take what's working for GPUs on CPUs. This is purely a CPU based. All my research is going to be on CPU. I really don't care about GPUs at this point in time, I'll be honest. But for me, when you're designing these types of things, you really need to understand the L3, L2, L1 cache, how that how the data is streaming through all of the memory from DRAM, and this separation allows that additional speed. And then we'll go to the attention heads. And here what we have is I'll just share where we are. Just give me a second. Let's go ahead. I've written many different types of, if you go to the code, you'll see all the different types of combinations I've done with memory layout. So it's not something that I'm just, coming up on top of my mind. A lot of this is done through tremendous amount of benchmarkings from microkernels, understanding whether I'm doing ahead from after the layer norm. Go check out, line number 1506. And here from onwards, you will see all the different ways of how I've been using, different configurations of token parallel, block parallel, QAV projections, whether I want to do it with head, without concatenation, with concatenation. So a lot of experimentation has gone into how I made this work. So this is the code. Everything is for high performance compute. So everything is going to be using single instruction, multiple data. So here I'm using the AVX-512 instructions. Here we're loading for the packed single precisions, and then we do fuse, multiply by add. It's all once you read it, it's pretty straightforward. I do use a lot of AI to help me write the boilerplate code, but a lot of my intuition and design and pseudocode is pretty much written by me. But writing every single detail in AVX-512 is not particularly fun for me, but it's necessary to write. So this is where I do use AI to augment a lot of my thinking. And then here and also the commenting and making it look more kind of like explaining what's there in my brain onto the physical world and paper. And this is where the AI augmentation is absolutely brilliant, because I write all of these things down and I'm like, can you present this to me? And it'll give me this nice little comments. So go ahead over here, use AI when it augments your thinking. And here I do things like convert token major to head major and see how that works. And then we benchmark all the different types of comparison. So a lot of research going on and just benchmarking. There are many details to this whole process. And once we benchmark, I can see which works better and the overall process. And then again, I've done another attention. So there's a lot of attention based computation over here, from token major to head major, seeing what the difference is. So there's around like 2,000-3,000 lines of code just on with comments and benchmarking to kind of like tell me what's working better and not. And then I run a small little benchmark over here, and this is what the benchmarks would run and how they would look. So in this particular case, I'm running all the benchmarks from layer norm to everything that's out there, and it will tell me that when I'm doing, the token major versus head major, what is my, it's taking me around, 3 seconds or, 33 seconds. And if I'm doing, from token major to head major with a different type of configuration, what's the speed, what's the accuracy from a naive approach. So a lot of numerical precision, checking for performance. So there's a lot of research going in the way I'm kind of like, figuring out how to do this in the right way. So have a look at this code. And if you have an Intel or any CPU that has the AVX-512 instruction set, I think you get a good understanding of how all of this works. So let's get back to our slide. Is the performance analysis and the real numbers. And this is all based on some benchmarks that I've done. And I'm kind of like extrapolating that we're getting pretty high cache, hits over here, because each time I make a configuration, I can see how slow it gets or how fast it gets. And it's pretty much, I can almost conclude that's got to do with the way the caching is working and how well the CPU is streaming all of this data. So here, I'm just giving you certain things can take, 0.3 milliseconds, 1.2 milliseconds. I'm tracking all of this based on the CPU that I have. It's also running on Kubernetes. So, put those things into context. So it may not be as fast as saying, hey, my local computer might be faster. But in many cases, the kind of like performance that I'm trying to do is squeeze everything out of a 6-year-old Xeon in some shape or form and how much performance I can get. And here there's a lot of future optimization, like, direct stride projection. Looking forward, we can optimize further by eliminating the phase 3, which is the concatenation. Currently, we do have a 4 process, which is QKV to head major, then attention, then concatenation to token major, then final projection. And in the future, we could have just 3 phases, just QKV to the head major, then attention, then direct stride projection. And this would eliminate the memory reorganization overhead in phase 3 by doing strided writes directly from head major attention output. An expected improvement could be around 10 to 15%, something that I would test again. It's all benchmarked. A lot of benchmarking is going on in here. This is not just, me speculating, just writing a lot of different types of code to see which one works better. So there's a lot of research going in that aspect. And this optimization is more complex to implement, but could push us even closer to the theoretical peak performance. And here we go to the finals phase. And I'm just want to talk about more about, the philosophy of why attention even works in this particular case. So here I want to just talk about, what is the genius of QKV? We've spoken about high performance, we've spoken about QKV, all the math, but let's, roll back a little bit. And this is something that I love a lot, is why do you need to put QKV and not put, some other formula in there? And what is it looking for? And for me, I've written these small little infographics to really truly understand, what's really happening. And when we do a question like, what I'm looking for, examples of learning queries, find my subject, find descriptions of me, find related concepts of me, find my verb. So the QKV is kind of like, doing what am I looking for, what I offer or advertise, and what I contribute. So this is the kind of like, thing of, it comes from a database implementation, but the beauty is that the backpropagation emerges these properties. You don't hard code QKV, it's emergent out of the backpropagation. And that's just the beauty about how, the AI works and how, the whole thing works. So the emergent is how attention learns relationships, how a cat and the cat or the sat or the mat, kind of like they work together. And then the multi-head attention, different heads learn different relationships. And then here you can say learn to concat, so learn to connect. So cat strongly attends to sat, or the strongly attends to cat, or cat attends to mat, and things like that. So here is the attention weights and the evolution across layers from syntax to syntax. So each layer might do certain parts of this whole evolution. So the quick brown fox attends is mostly local. Then we have the cat that sat on the mat, attends sparse, spans phrases. And then, you could say that it was comfortable, attends to task specific, and predicting the next word, attention is highly selective at this point in time. So each layer does a different types of interpretation, and emergent properties emerge while we, do the attention. So attention is where, the grammar, the meaning, the semantics, all of it, kind of like emerges in the backpropagation. And we are doing a lot of optimization as well. So in this particular case, during the attention training, the induction head pattern matching, the cat sat on the mat, the dog sat on and the model learns after the dog sat on the predict the mat. So we're not explicitly programming, but these are all emergent properties of this particular computation. And then the dog's R is barking, the head learns, plural, subject plural verbs, and the tracking, it's tracking the numbers, it's tracking the gender, the tense, it emerges earlier, and then it can kind of like, progress to the other layers as well. and then knowledge retrieval or understanding who did what to whom. And all of this is all emergent. And why my C implementation enables better understanding, because first and foremost, when you write from the grounds up, you truly understand what's happening. And then, I can start putting all of these attention patterns and kind of like visualize all of these things and do things like mechanistic interpretability and all that cool stuff. So writing in C with all of those benchmarks, you can already see the value of what you can get from writing all of this from the grounds up. And then the problem is the cat sat on the mat because it was soft. And what does it refer to? The cat on the mat. And also what attention is doing is kind of like taking the mat and attending to different tokens previously. The tensor dimension is important when you're doing all this computation. And how the AVX-512 kind of like makes all of this work. We take this from QKV Projections, we create the attention score, then we apply the Softmax, and then we do the weighted sum, and then finally we do the final projection. All of this is all really, it's actually very fascinating, but again, this is very high level, this is very, high performance compute is the focus over here, but the emergent properties of what's happening, we can introspect by writing all of this from the grounds up. And the AVF optimization opportunities, this is what we've just taken advantage of all the scalar operation. It's a 2D optimization. When we use AMX, which is a more recent instruction set from Intel, then we could take care of 3D, this is 1D tensor computation, and we could take care of 2D tensor computation with later instruction sets. And let's look at the attention mechanism and kind of like from an HPC deep dive. This is the recurrent neural network of token 1, token 2, and they don't really attend to each other. Whereas self-attention, kind of attends to each other. We take the embedding dimensions, which is context length by the dimensions of the embeddings. We generate the QKV projections. Then we do the QK and V, which is of shape context length by the head dimensions, context length of the head dimensions. We do the query and key transpose, apply the softmax. Once we get the attention score, we multiply that by the value scores. And for all the heads, we basically concat everything back together, and then we take the attention output, which is again context length by embedding dimension. At this point in time, I've done this so many times that I pretty much can do this in my sleep. At this point in time, muscle memory kicks in very quickly. And then with all of these AVX instructions, you have fuse multiply by add with packed single precision, and then you get your system. That's really it. So the complete journey, we've traveled from fundamental mathematics to production grade high performance code. Our mathematical understanding includes scale dot products, attention, multi-head processing, casual masking, and flop analysis. Our conceptual intuition covers head parallel strategy, memory layout transition, cache optimization, and AVX-512 vectorization. Our memory architecture uses single allocation strategy, head major layout, precise offset control, and canary protection. Our HPC and production implementation achieves around 400 gigaflops performance, 96% L3 cache hit rates. At least I'm thinking we're getting pretty high. Of course, we're running on Kubernetes, so these numbers, something that I need to kind of like be cautious of, because I should be putting VTune to really see this. But I don't know, the speed is very noticeable. And this is all production ready C code with a lot of different types of benchmarkings and the full transformer integration. So this is the complete transformer from theory to world-class. I'm thinking it's world-class implementation because I've not seen anything of this sort before. So I'm pretty happy with the way this is progressing. And that's really it. We've gone from mathematical rigor to concept clarity to the memory architecture to HP performance and production ready. So let's deploy the high performance AI inference, right? And that's it for us today. And in the next video, we're going to do the full inference, the code, making the working code. I've already got everything working. The inference is working. The speed is pretty good. There's still a lot of other things that I need to work on, as KV caching and all the other cool stuff. But I can show you the full parity with PyTorch, the numerical parity. GPT-2 is not the best in terms of LLM, in terms of output. But what I'm trying to show you is the actual whole process, because everything now scales from there to modern day AI. And I can't wait to show you that inference. If you like all of this, subscribe, please like the video. And until next time, please take care. Thank you.